Hey, natural science students, I'm going to go ahead and preemptively strike the possibility of a snow day tomorrow by recording what we're intended to accomplish in large group on Tuesday so that you can look over this in the inevitability that we do have a snow day. Because the part of the reason why we're doing the egg drop is, of course, for you to have an opportunity to practice design skills and designing within constraints and having limited materials to do a design, and all that stuff from a scientific and an engineering standpoint is very important. But we also want to connect this to the science, and that's going to be the big focus of today, to make sure that we have a completely comprehensive review of all the science that is involved with egg drop physics. And so what I'm going to do here is I'm going to start off with a scientific principle that should be very easy for us to understand, and that is gravity. And I'm going to work through all the aspects of how these different scientific aspects are being used in the egg drop. And so let's start out with gravity. Okay, just some reminders to get us started that gravity is a pulling force, and we want to make sure that we get the direction right. It is towards the center of the earth, not down. If it were down, you'd be standing on Australia and you'd fall off the earth, and we know that that doesn't happen. Gravity attracts two objects to their centers based upon their mass. And the Earth is a really massive object that pulls smaller objects like you and me and the egg drop device towards its center. Now, it's not just a pull in a certain direction. That pull is exerting a force that is accelerating objects. So gravity accelerates objects, making them move faster. This also means, another way of saying that, is that they have a higher velocity. By the way, friends, for this video I'm using the Pentel Quicker Clicker vintage model, which has the smooth plastic barrel. This one's probably from the 1990s. You can tell that it's a vintage model because old green Pentel eraser. It's like writing with a stick of butter. I'm just throwing that out there. Okay? And we can add a specific number to this acceleration. The specific acceleration is 9.81 meters per second every second. So every second that you fall, you get 9.81 meters per second faster. This is why people get into trouble when they fall. Now, we have a big misconception alert that I want to address here, because I've heard this a lot over the last couple of days. And I want to make sure that we have an opportunity to address this so that you're aware of what we should be, a common pitfall that people have when they're thinking about this. And that misconception is that people think, and this is not true, well, it's partly true. Heavier objects do not fall faster. Now, the acceleration of gravity between two objects is greater with greater mass. That is true. And so there is a not measurable difference between dropping an egg device and dropping a person, or dropping a car, or dropping a building. All of those objects compared to the scale of the Earth are so small that we don't notice the difference between their acceleration. So there is a difference, but for our purposes, for different egg devices, a heavier object is not going to fall any faster than a slightly lighter object. Now, this does relate to momentum, which we'll talk about here in a little bit. Okay, momentum is a worry during a collision. But during the actual falling of these objects, momentum is not going to be a problem. And momentum is affected by a greater mass. So we're not saying that mass doesn't matter here, but we want you to understand under which context mass matters. Okay, so that is a pretty thorough description of how gravity affects the egg drop device. Let's go on to the next concept that we have here. And our next concept is the concept of air resistance. Okay. Remember, all air resistance is it's a form of friction. objects rubbing up against other objects that are essentially acting as forces that changes some aspect of their motion. And friction and everything associated with it is governed by Newton's second law of motion. Erase, erase, erase. Second law of motion. And there is an equation that helps to describe Newton's second law of motion. That equation is that force is equal to mass times acceleration. If you decrease the amount of force acting on an object, okay, like the force of gravity pulling on the object, you lower its acceleration. So in this case, what air resistance is doing is air resistance is causing an object to move slower and you can do that with a bunch of different devices. You could use a parachute, true, or you can use anything that increases or decreases the surface area. Of the device. And I'm going to try to illustrate that for you here. If we compare this box to this box, this is more area that air could rub up against. Let's go ahead and diagram this in the little gap that we have here. So let's say that the person, notice how I drew a fun stick figure with a freakishly long arm. Let's say that this person drops the egg device. There's the egg in the device. Sorry about the bell. Okay, we have two forces that are acting on this egg. We have the force of gravity pulling it towards the center of the earth, and we have the force of air resistance or air friction pushing back up on it. So these two aspects are fighting each other. Now, as that device continues to fall, there's also going to be effect on the momentum of the device as it falls. As the device falls, it gets faster. We know that it's going to get faster because even with the concept of air resistance working against gravity, air resistance is never going to counteract the pull of gravity. At least not with the materials that we have available in this lab. And since it gets faster, it has more momentum. Remember our equation for momentum. Momentum, represented by the Greek letter rho, looks like a shepherd's hook or kind of like a letter P, is equal to mass times velocity. Okay, I'm going to go ahead and move it up a little bit. So we have plenty of space here. Okay. 100% of the momentum gets transferred into the ground when the device hits. Students, I can't make you take notes on this. I can't force you to do anything, but I'd like you to seriously consider, if you haven't already gotten out a sheet of paper and watching this video, to take out a sheet of paper and try to replicate this piece of paper as best as you can, because the mere action of writing these things down could help you to have a stronger grasp on all the science, the physics behind the egg drop, because at the end of this week, and into next week on Monday, you will be required to prove to us that you understand all the dimensions of the physics of the egg drop. We're not just doing this for an engineering experience or for a fun experience, although hopefully those two things should be happening. We're also doing it because we want you to understand the science of it, because, folks, this is just like a car crash that happens up and down instead of side to side. And by understanding the nature of all these laws, it can help to make you safer. Now, there's some of Newton's laws that we haven't talked about yet, and that is, let's go to Newton's first law of motion. I should probably point out here real quick, this momentum increase is happening while the device is still falling. So here's the device, it's still falling. The momentum, the Greek letter rho, is increasing as it falls. Now let's start to talk about what happens when the device strikes the ground. So I'm going to move this up even a little bit more, and I'm going to draw a ground level here. Here's my ground level, and I'm going to draw the device striking the ground. Wha-bam! Draw in the egg device, draw in the egg device. Got a little parachute to help with air resistance. So when this device strikes the ground, strikes. Actually, I want to take a step back. Instead of when the device strikes, when the device is falling, both the egg and the device are in motion. We have another misconception here. Okay, a big misconception people have is that when I'm riding in the car, I'm still. To you, you appear to be still because you have a certain frame of reference. But trust me, friends, when you're in a car and the car's moving, you are moving with the car, just like the egg is moving with the device as it falls. Okay, so both the egg and the device are in motion when it's falling. Now, when the device strikes the ground, the device stops. But Newton's first law of motion tells us a little bit about the egg. Since objects in motion tend to stay in motion, unless acted on by an unbalanced force, the egg will tend to keep moving even though the device has stopped. Uh-oh. Remember how we said unless acted on by an unbalanced force? The ground can be that unbalanced force. And speaking of forces, now we need to talk about Newton's third law of motion. For every action force, there is an equal and opposite reaction force. The action force is the egg device and potentially the egg striking the ground, pushing on the ground. The reaction force, remember these arrows are drawn tip to tip. The reaction force is the ground pushing back up. And that's where your egg is in danger. We'll talk more about this collision in a second. I'd like to point out at this stage that that transfer of momentum that we talked about up here, that is the action force. Okay, 100% of the momentum gets transferred, and it's being transferred as the action force for Newton's third law of motion. Now, the good news is that we don't just have to accept all that force being transferred all at once as part of that collision. And so I'm actually going to go to the back of the paper here. Okay. How you experience those action and reaction forces makes a difference for egg breakage. Specifically, this is related to the scientific concept of impulse. The longer a collision lasts, the more spread out the action force is over time. So you can take that action force, bam, like a car hitting a brick wall. Or you can take that action force more like your face going into an airbag. So things like seat belts, which stretch just a little bit, adding time to the collision. You get a higher impulse. Airbags, smoosh, adding time to the collision. Crumple zones, the front of your car or maybe the bottom of your egg device, are designed to smoosh, adding time to the collision. And if a number example is something that's going to help you out a little bit more, here's a number example. Let's say that the action force, which leads to a reaction force in the collision, were 1,000 newtons. You can either take that 1,000 newtons all at once, or you can take that 1,000 newtons. You can't stop yourself from taking the 1,000 newtons. It's happening. The law of conservation of momentum says that all that momentum gets transferred in the collision. But instead of taking that 1,000 newtons all at once, what if you took 200 newtons spread out over 5 milliseconds? That's going to be a lot better for you. So think back to your egg device. Think back to all these examples of how this relates to the science. And if we end up not having school tomorrow, you'll be expected to have been watching this video. And if we did have school on Tuesday, then I will be seeing you in large group instead. Thanks for watching.